Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins our task. The year 1748 witnessed the publication of a monumental text, Introduction to the Analysis of the Infinite, authored by Leonhard Euler. This treatise, far from being a mere introduction, effectively charted new territories within mathematics, establishing the function concept as central and providing a thorough exploration of infinite processes. This essay undertakes a detailed evaluation of Euler's claims within this foundational work, moving sequentially through its core components to assess the arguments presented and their lasting impact. We examine the specific arguments without relying upon simple contrast of language. Section 1, concerning quantities variable and constant. Euler begins his exposition by establishing the fundamental distinction between variable and constant quantities. Euler posits that a constant quantity maintains a fixed and unchanging value throughout a given mathematical undertaking, while a variable quantity is capable of assuming different values. This initial demarcation, seemingly straightforward, lays the groundwork for the entire edifice of analysis. Euler argues the essence of mathematical analysis resides in the manipulation and investigation of these variable quantities and their relationships. It is here that Euler introduces the concept of a function, not yet with the modern rigor of set theory, but rather as an analytical expression formed in some way from variable quantities and numbers. Euler asserts that any quantity whose value depends on a variable will invariably be a function of that variable. This assertion, while intuitively appealing, requires further scrutiny as Euler's understanding of dependence is initially tied to explicit algebraic expressibility, a limitation that would later be so. He then begins to explore the notion of continuous variability, that a variable can pass smoothly through an infinite number of intermediate values. Euler also acknowledges that this process of continuous change and the acceptance of numbers which could be infinitely large or small was quite controversial for people of the period. The acceptance of these concepts was critical given that Euler would soon begin discussing algebraic functions and geometric applications of the new infinite analysis. Euler's initial claim concerning variables and constants, while seeming elementary, crucial for understanding the subsequent development of his analytical method. Section 2, concerning functions in general. After setting the stage with variable and constant quantities, Euler dedicates considerable attention to establishing the nature and properties of functions. Euler classifies functions into algebraic and transcendental categories. Algebraic functions, in Euler's view, are those formed through the standard algebraic operations of addition, subtraction, multiplication, division and root extraction. Transcendental functions, on the other hand, encompass all functions that cannot be expressed in this manner, including exponential, logarithmic, and trigonometric functions. It is important to acknowledge that Euler's definition of a function is more expansive than modern definitions. For Euler, any expression involving variables, regardless of its analytical properties or well-definedness, could be considered a function. Euler claims that functions can be expressed explicitly as an expression built up with the normal algebraic operations, or implicitly, which define a relation between variables. The definition serves to include objects, which are not necessarily well-behaved and may not even be continuous at every point in their domain. Euler emphasizes the importance of studying the behavior of functions as their arguments approach infinity or zero. He posits that understanding these limiting cases is crucial for uncovering the essential nature of functions and their relationships. This claim is borne out by the subsequent development of calculus, where the concepts of limits and derivatives are fundamental. Euler demonstrates a keen awareness of the potential for functions to exhibit singularities or discontinuities, points where their behaviour becomes irregular or undefined. While he acknowledges these irregularities, his primary focus remains on the more regular and well-behaved functions that lend themselves to analytical manipulation, the classification of functions, and the emphasis on limiting behaviour exhibit Euler's goal of bringing order and structure to this nascent field of mathematical analysis. It is an ambitious undertaking, setting the stage for his subsequent explorations of specific function types. Section 3 concerning the transformation of functions. Having established a framework for understanding functions, Euler addresses the transformation of functions. Euler asserts that functions can be transformed in various ways without altering their fundamental nature. He argues that these transformations are essential tools for simplifying complex expressions and for revealing hidden relationships between functions. Among the transformations Euler considered, substitution is central. Here, one variable is replaced by an entire function of a different variable. This allows for complex equations to be simplified. Euler demonstrates a mastery of algebraic manipulation, showcasing his ability to transform functions into equivalent forms that are more amenable to analysis. Euler claims that through strategic transformations, seemingly intractable problems can be reduced to simpler, more manageable ones. For example, Euler explains the importance of transformations which remove rational denominators from functions. Euler's assertion of the transformative power of algebraic manipulation is a recurring theme throughout the work. His facility with these techniques is undeniable, and his examples serve to illustrate the practical utility of these methods. Section 4 concerning exponential and logarithmic functions. Euler dedicates considerable attention to a thorough treatment of exponential and logarithmic functions. He asserts that these functions are fundamental to mathematical analysis, playing a crucial role in a wide range of applications. Euler provides a comprehensive treatment of the properties of exponential and logarithmic functions, including their derivatives, integrals, and series representations. He emphasizes the inverse relationship between these two function types, demonstrating how each can be expressed in terms of the Euler uses the exponential function to bridge exponential and trigonometric functions through the complex logarithm function. This is one of Euler's single most impactful claims, and would forever change the face of trigonometry and complex analysis. Euler's exploration of exponential and logarithmic functions is notable for its rigor and completeness. He provides detailed derivations of key formulas and identities, showcasing his mastery of analytical techniques. Section 5 concerning transcendental functions arising from the circle. Euler moves to the investigation of trigonometric functions. He posits that trigonometric functions are essential for describing periodic phenomena and for solving geometric problems. Euler provides a comprehensive treatment of the properties of trigonometric functions, including their derivatives, integrals, and series representations. Euler asserts the ability to express trigonometric functions in terms of exponential functions with imaginary arguments. This is an early foray into complex analysis, where complex numbers are used in conjunction with trigonometric functions. Euler demonstrates how trigonometric functions can be used to solve problems in geometry and mechanics. Euler claims that the trigonometric functions offer a pathway to model many real-world phenomena. This is a bold statement which shows Euler's vision for applying the theory to real-world examples. He also delves into the computation of trigonometric tables, providing methods for calculating the values of trigonometric functions to high degrees of accuracy. Section 6 concerning the development of functions into infinite series. Euler shifts his focus to the development of functions into infinite series. He asserts that representing functions as infinite series is a powerful tool for approximating their values and for analyzing their behavior. Euler provides a detailed exploration of various methods for expanding functions into infinite series, including Taylor series, Maclaurin series, and Fourier series. These methods are crucial to many applications in math, physics, and engineering. Euler claims that functions, under certain assumptions, may be represented by a power series, and his demonstration of methods to generate such series forms a large part of this section. Euler emphasizes the importance of convergence, noting that not all infinite series converge to a finite value. He provides criteria for determining whether a given series converges or diverges, and he cautions against blindly applying series expansions without considering their convergent properties. Euler is very careful to denote situations when results may only be approximate. Euler's exploration of infinite series is a testament to his analytical skills and his deep understanding of the properties of functions. Section 7 concerning the summation of infinite series. Euler extends his discussion to the summation of infinite series and claims that methods to sum series can expand the class of problems which can be solved analytically. He posits that finding close-form expressions for the sums of infinite series is a challenging but rewarding endeavour. Euler explores a variety of techniques for summing infinite series, including telescoping series, geometric series, and power series. He provides numerous examples of series that can be summed explicitly, and he demonstrates how these sums can be used to solve problems in analysis and number theory. Euler acknowledges that many infinite series cannot be summed in closed form. He introduces methods for approximating the sums of these series, and he discusses the limitations of these methods. Euler asserts that understanding the convergence of a series is important. This is clearly a nod to the famous Basel problem, which he solved earlier in his career. Euler's treatment of the summation of infinite series demonstrates his profound understanding of the properties of series and his ability to manipulate them to obtain meaningful results. Section 8 concerning the resolution of equations. Euler proceeds to the subject of equation resolution and claims that finding the roots of algebraic equations is a fundamental problem in mathematics. Euler explores a variety of methods for solving algebraic equations, including factoring, the quadratic formula, and numerical approximation techniques. He discusses the limitations of these methods, noting that many equations cannot be solved explicitly. Euler introduces the concept of complex numbers and demonstrates how they can be used to solve equations that have no real roots. He claims that the introduction of complex numbers expands the toolkit available for solving polynomial equations. Euler's treatment of equation resolution illustrates his mastery of algebraic techniques and his deep understanding of the properties of complex NA. Section 9 concerning maxima and minima. Euler turns his attention to the problem of finding maxima and minima of functions. He asserts that finding the extreme values of functions is a crucial problem in optimization and calculus. Euler provides a detailed treatment of the methods for finding maxima and minima, including the use of derivatives and critical points. He demonstrates how these methods can be used to solve problems in geometry, mechanics, and economics. This includes discussions of optimization problems and constrained optimization. Euler emphasizes the importance of considering the second derivative test to determine whether a critical point corresponds to a maximum, a minimum, or a saddle point. He cautions against relying solely on the first derivative test, as it may not always provide sufficient information. Euler claims that the process for finding maxima and minima of functions is critical for many different applications. Euler's discussion of maxima and minima demonstrates his deep understanding of calculus and his ability to apply it to a wide range of practical problems. Section 10 concerning curvilinear figures. Euler concludes his seminal work with a consideration of curvilinear figures. He posits that understanding the properties of curves is essential for understanding geometry and calculus. Euler provides a detailed treatment of the methods for finding the area, arc length, and curvature of curves. He demonstrates how these methods can be used to solve problems in geometry, mechanics, and physics. Euler addresses the representation of curves using both rectangular and polar coordinates. Euler emphasizes the importance of considering the orientation of curves, as this can affect the sign of the area or arc length. He also discusses the concept of envelopes, which are curves that are tangent to a family of curves. Euler asserts that understanding the properties of curves is a powerful analytical tool. Euler's consideration of curvilinear figures provides a fitting conclusion to his introduction to the analysis of the infinite, demonstrating the power and versatility of the analytical methods he has developed throughout the work. In conclusion, Euler's introduction to the analysis of the infinite represents a landmark achievement in the history of mathematics. Through careful categorization and deep analysis, it laid the foundations for modern calculus and analysis. While some of Euler's initial definitions lacked the rigor of later formulations, his insights and techniques proved immensely influential, shaping the course of mathematical development for centuries to come. His work is a testament to the power of analytical thinking and his unwavering commitment to exploring the infinite.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.